Alright, welcome. In this video I'm going to be working Linear Algebra Homework 6.1, which is all about 2x2 eigenvalues. So the first few are just like, hey, find the eigenvalues and the eigenvectors for this matrix. So well, we can do that. So we know that it always starts off with finding the solutions to a minus lambda times the identity equals 0. And any lambda where that could potentially work, that'll be an eigenvalue, and then the types of vectors that form the null space of a minus lambda I, pardon me, not a minus lambda I equals 0. A minus lambda I times a vector x is equal to the 0 vector. Okay. So what we're going to do is we're going to start off with a minus lambda I. And that's going to be 2 minus lambda, 1, 1, and 2 minus lambda. I'm going to find the determinant of that because if this thing is going to have interesting solutions, like interesting x values to that equation on the left, then this matrix here is going to have to be singular. And one of the conditions for being singular is that it has a 0 determinant. So we're going to say that 2 minus lambda multiplied by 2 minus lambda minus 1 times 1, that needs to equal 0. And that's going to be a secondary polynomial that we can probably solve. So if I square 2 minus lambda, I'm going to get lambda squared minus 4 lambda and positive 4. And then I'm going to subtract 1. And this is factorable with, I think, lambda minus 3, lambda minus 1. Okay. So that means that my eigenvalues are going to be lambda equals 3 and lambda equals 1. Kind of within those, I'm going to need to give myself a little more room to work. Okay, those are the eigenvalues. Now we'll need to find the eigenvectors. So a minus lambda I, in this case, is going to be a minus 3i, is 2 minus 3, 1, 1, and 2 minus 3. Okay, if I was to row reduce this to find the null space of this matrix here, because that's what I'm looking for to find these x's, then I'm going to row reduce the thing, and I'll get 1, negative 1, 0, 0, and if I'm trying to find the null space, this will be, okay, where x1 minus x2 equals 0, so x1 equals x2. Still a little bit more room. And my eigenspace, or my eigenvectors, is going to be the set of all x's for which x is some multiple of the vector 1, 1, because it's x1 is equal to x2. And I think, yeah, that'll be far enough for us. Then for lambda equals 1, I'm going to take a minus lambda I, so that'll just be a minus 1i. It's going to be 2 minus 1, 1, 1, and 2 minus 1. So I go to row reduce this the same way. And I guess I'm interested in finding the null vectors there. And so this would be x1 plus x2 equals 0, so x1 equals negative x2. And then my eigenspace, or my eigenvectors, are going to be the set of all vectors where, you could say where x1 equals negative x2, that would be fine, or you could say x is some multiple of 1 and negative 1. And maybe we'll give it the other curly brace to make it a set. Okay, that's all we got to do for that one. And on the second one, we're going to go to a minus lambda I. That would be 1 minus lambda, 0, 2, and 3 minus lambda. And then this will be easy to take the determinant of because of that 0 up in the top right. So we need the determinant of a minus lambda I to equal 0. And so that'll just be 1 minus lambda multiplied by 3 minus lambda equaling 0. Okay, so it's already factored. We're good to go. Lambda equals 1, lambda equals 3 again. Okay, so with lambda equals 1, I'm going to say a minus lambda I is 0, 0, 2, 2. And, okay, that would reduce to 0, 0, 1, 1. I'm going to do a row swap to get it in a fully reduced form, but this is good enough to find the null space, right? So we're going to say x1 equals the negative of x2, I guess. And so then maybe with this one, I'll write the eigenvectors. Okay, if I'm going to just write it in terms of an equation, I need to say this is the set of all two-dimensional vectors for which x1 plus x2 equals 0. And that would be all right. That would be just fine. Because they didn't ask you for a basis for the eigenspace. Okay, that was kind of what I did up here. But maybe not exactly. That 1, 1, and 1, negative 1, those would each be a basis for those respective eigenspaces. Okay, so that's lambda equals 1. With lambda equals 3, I'm going to say, okay, I'm going to say 1 minus 3 and 3 minus 3. Okay, okay, so what this is going to be is if I row reduced it all the way, I'd get 1, 0, 0, 0. And this is one that I noticed where there was one like this on the recent test, and this was kind of a situation that we had, it's not hard, but we didn't think it all the way through. So if I have this, I'm going to kind of decode this equation right here. This is 1x1 plus 0x2 equals 0. So that just means that x1 needs to equal 0, and x2, there's not really any rules on what that's going to be. So x2 can be whatever it wants. And so the only restriction here is going to be the first component is 0. All right, number 3, 1, 2, 4, 8. This one's already singular, so we're going to see that 0 is going to be an eigenvalue of this thing. Okay, so we are going to go to a minus lambda I. It's going to be 1 minus lambda, 2, 4, and 8 minus lambda. Okay. So if I want the determinant of a minus lambda I to equal 0, then that's going to be 1 minus lambda multiplied by 8 minus lambda minus 2 times 4. That needs to equal 0. And if I were to, multiply this thing out, I would get a lambda squared. Negative 8 lambda minus another lambda is going to be minus 9 lambda. And then plus 8, and then immediately minus 8, that needs to equal 0. So, okay, I'll do that. Factor. So I get lambda equals 0, and lambda equals 9. Okay, lambda equals 0, if you see that, you see 0 as an eigenvalue, then you know your matrix is already singular. Okay, and if you think about it, lambda equals 0 is that thing where you take a non-zero vector and you hit it with a on the left and it goes to the 0. Okay, well that's what it means to be in the null space, so okay, lambda equals 0 is not that interesting of an eigenvalue. Okay, for lambda equals 0, we're going to just row reduce a without adjusting it. So that'll be 1, 2, and then if I subtracted 4 copies of row 1 from row 2, I'd get that. And I would say, all right, x1 plus 2x2 equals 0. x1 is negative 2x2. So the eigenvectors would be the set of all x such that x is some multiple of x1 is negative 2 times x2. So I'm going to make that 1 and this negative 2. For lambda equals 9, I'm going to be interested in the null space of a minus lambda I. So 1 minus 9 is negative 8 and 2. 4 and 8 minus 9 is negative 1. Okay. And, if we were to row reduce this, I think I might subtract add 2 of row 2 to row 1, and then that would just be kind of my thing I'm going to use. And I'm going to need more space here. Okay, yeah, that's good. So 4x1 minus x2 equals 0. That means x2 is equal to 4 times x1, and my eigenvectors are the set of all x's for which x is some multiple of 1 and 4. Yeah, because x2 is 4 times x1. Okay, number 4, the last one of these. We're going to go to a minus lambda I. And that's going to be 3 minus lambda, negative 1, 5, and negative 3 minus lambda. I guess I don't need those. And then I'm going to find the determinant of a minus lambda I, and I'm going to set that equal to 0. So this determinant is going to be 3 minus lambda times negative 3 minus lambda minus negative 5. That needs to equal 0. Right, so I'm going to have a positive lambda squared. Negative 3 times negative lambda is positive 3 lambda. Positive 3 times negative lambda is negative 3 lambda. If I multiply 3 times negative 3, I get minus 9 plus 5. That's going to be lambda squared minus 4 equals 0, and we can factor that. Okay, and now I've got my eigenvalues, 2 and negative 2. Okay, so for lambda equals 2, I'm going to take a minus 2i. 3 minus 2 is 1, negative 1, 5. Negative 3 minus 2 would be negative 5. I'm going to row reduce this and read off the null vectors. So x1 minus x2 equals 0. That means x1 and x2 are equal. And I would say that my eigenvectors, well, didn't go well. Again, a little too zoomed out, I think. And, okay, so it's the set of all x in R2 for which x1 and x2 are equal. And we've seen that space a couple of times so far. Right, so then I'll give myself a little more room and do lambda equals negative 2. 3 minus negative 2 would be 5. Negative 1, 5. Negative 3 minus negative 2 would be negative 1 again. So if I row reduce this, I'll just get 5, negative 1, 0, 0. I'm interested in the null space of that matrix, so I'm just going to augment with zeros and interpret my solution. So I'll have from this equation right here, 5x1 minus x2 equals 0. So x2 is equal to 5x1, and so I would say this is the set of all x in R2 for which, or you could even just write the equation, 5x1 minus x2 equals 0. Okay. And that's all for those problems. All right, now this next one wants you to just find the eigenvalues for the matrix, not the eigenvectors, and I feel like that's probably because these are going to come back complex. And although we can find the eigenvalues when they're complex, we're in this class not going to be dealing with the eigenvectors that correspond to complex eigenvalues. If you're interested in that, you should definitely take a linear algebra class at the next school you go to, right, at the university level. Or hit the World Wide Web and look up what happens when eigenvalues go complex, because I'm sure that there's a lot of stuff out there for you. We're just not going to hit that in this class. So we're going to do the exact same thing. We're going to go over here and we're going to say, all right, a minus lambda I is equal to negative 2 minus lambda, negative 1, 5, and 2 minus lambda. Okay. So the determinant of a minus lambda I, we're interested in where that would equal 0. So that would be the negative of, I'm going to actually factor out the negative from negative 2 minus lambda and call that 2 plus lambda, because I noticed this happened last time. And so minus negative 5, that needs to equal 0. Yeah, because the way it multiplied out, it was kind of a lot to keep track of, but it ended up stuff canceled off as a difference of 2 squares. So I just figured I'd make this happen again, make it a little easier to look at. So this is going to be the negative of 4 minus lambda squared plus 5 needs to equal 0. And so I'll get a positive lambda squared, a negative 4, and a positive 5. And lambda squared plus 1 equals 0. So lambda squared equals negative 1. Okay, if I take the square root of both sides of this equation, then I'd get the absolute value of lambda equals the square root of negative 1, which we call I. You might not have called it that for a couple of years, because we don't talk about that in AP Calculus. But if the absolute value of a number is equal to I, then in the number itself will either be plus or minus I. Okay, and these are my eigenvalues, and we see that these are not real numbers. Okay, but that's possible, and it has significance. We just aren't getting into it in this class. All right, now these next couple, these are pretty beefy. So this is kind of a taste of, types of problems you might be expected to do in a really mathy linear algebra class at the university level. Lots of show that or prove that type problems. So what we're going to do is, I think we're just going to compute the eigenvalues as if there's nothing wrong here. U and W and V will just treat them like numbers and just keep investigating, and it'll shake out. I know for a fact that this one will because I worked it yesterday in class. So let's just get right to it. So m minus lambda times the identity is going to be equal to u minus lambda, v, and w minus lambda. If I take the determinant of that and set it equal to 0, let's see, u minus lambda multiplied by w minus lambda minus v squared, that needs to equal 0. Okay, and at this point, I don't know if, I can't see any reason why lambda has to be real looking at this equation. So we're just going to need to keep going. First, outside, inside, last, minus v squared equals 0. And if you're not seeing anything to do with this, what you should do is try to, like, this is a secondary polynomial in lambda. U, v, and w are just numbers. Lambda is the variable. So let's just set it up. If necessary, we'll just use the quadratic formula. And I think that's what we're going to do. So lambda squared, that's the only lambda squared I see. In terms of just lambdas, I think I'm going to say plus negative u minus w times lambda to the first. And then the constants I have is plus uw minus v squared. That needs to equal 0. It's like, oh man, I don't know about this. But if we look at this, it's going to shake out. We know that what determines if a quadratic equation has solutions or not is the discriminant. So if we're thinking of a as 1, b as negative u minus w, and c as uw minus v squared, if b squared minus 4ac is greater than 0, then we'll always have real solutions to that equation, and therefore we'll have real eigenvalues. And I don't see it right now, but I can see that it's going to happen. So I'm going to kind of be interested in b squared minus 4ac. So negative u minus w squared minus 4 times 1 times uw minus v squared. And we're going to be interested in if this is a positive or a negative number. All right, so I'm seeing when I square negative u minus w, well, that would be the same as squaring u plus w, so it would be u squared plus 2 times u times w plus w squared minus 4 times u times w plus 4v squared. Okay, and then, well, that's a lot of stuff here, so I'm just going to collect all the squares. I know I showed that this was positive in class yesterday, so I know it's possible. Minus 4u and w. What is that going to do for me? I'm going to have to cheat and look at my work from yesterday. Okay. I'm realizing I did not bring that tablet home with me, and so I will not be able to cheat off of last time. But I am seeing that I made an algebra error here. When I took 2uw and subtracted 4uw, I need to have negative 2u and w, and now I see it. Okay. Now I'm going to rewrite this. Here it is. Okay, this was tricky. All right, this thing that I'm going to highlight in yellow, it's factorable. It's a perfect square. This is u minus w squared plus 4v squared. And regardless of what u and v and w are, if we combine them and square these numbers, like you square something, it's going to be positive, right? And provided that u, v, and w are not all 0, this will be greater than 0. And I think that, I don't know if there was a disclaimer in the statement of the question. No. Okay, but, symmetric non-zero matrix, then we're good. Okay, and so it has to do with, square numbers always being positive. That was kind of a wild ride. And the last one, I think this one's actually going to go down a little bit easier. And we're going to show that there are no real scalars where q minus lambda I is singular. Okay, so we're going to try to set the determinant equal to 0, and we're going to see it's not going to happen. So we're going to go over here, and I'm going to say, all right, q minus lambda I is equal to a minus lambda, b, negative b, and a minus lambda again. Okay. I'm also going to put off to the side that q minus lambda I is singular if and only if the determinant of that matrix is 0. Let's see if I can write that a little bit nicer. Okay, there we go. Yeah, it kind of fits. Let's shrink it down a little bit. Okay, so we're going to take this determinant here. We're going to say, all right, this is going to be a minus lambda squared minus b times negative b would be plus b squared. And, well, we're going to show that this equals 0 and hopefully arrive at a contradiction. Oh, yes, lambda is a real number and this equals 0. That will be contradictory. So I'm going to have a squared minus 2a lambda plus lambda squared when I square a minus lambda plus b squared. That needs to equal 0. So I'm going to again write this as a quadratic. And then, yeah, a squared plus b squared. And again, I'm going to label these as a and b and c, and I'm going to check b squared minus 4ac. Nope, a is 1, not negative 2a. So a is 1, c is a squared plus b squared. All right, and yeah, we're going to square that negative 2a, and we're going to get positive 4a squared minus 4a squared minus 4b squared. That's going to equal negative 4b squared. And negative 4b squared must be a negative number. If the discriminant is negative, we know that this quadratic, that I'm going to highlight in yellow, this quadratic equation, has only non-real solutions. Okay, so this means that because b squared minus 4ac is less than 0 for any value of a and b, it means that lambda is not a real number. Which is what I'd set out to show in the first place. All right, that's going to be all for this video. Thanks for watching.